The basics of motion. Here's our order, starting with vocabulary, our key takeaways, explanation of material, examples, and next steps. First up, the objectives. By the end of this lesson, you should be able to describe a scalar or vector quantity using magnitude and direction as appropriate. You should also be able to describe a vector sum in one dimension and describe a change in an object's position. To reach these objectives, the knowledge you're going to need are the scalars or quantities described by magnitude only. Vectors are quantities described by both magnitude and direction. Vectors are notated with an arrow above the symbol for that quantity. Little asterisk here. Vector notation is not required for vector components along an axis. As long as we are only working in one dimension, the sign of the component completely describes the direction of that component. More on that later. Distance and speed are examples of scalar quantities, while position, displacement, velocity, and acceleration are examples of vector quantities. There's more of each of those as we go throughout the year. When determining a vector sum in a given one-dimensional coordinate system, opposite directions are denoted by opposite signs. Displacement. When using an object model, the size, shape, and internal configurations are ignored. The object may be treated as a single point with extensive properties such as mass and charge. Displacement is the change in an object's position. Relevant equations, delta, that's that triangle, delta x equals the final x or final position minus x sub 0 or naught. In not, but not. N-A-U-G-H-T, not. So final minus the starting position. It's an easier way. Or initial position. We also have our velocity average equals our displacement divided by our time interval. Vocabulary to help you along here. Scalar is a quantity that is only associated with the magnitude. Magnitude means how big or how much. Vector is a thing with magnitude and direction. Oh yeah? That can be represented with an arrow whose length is proportional to the magnitude and points in the direction the quantity is headed towards. Direction is usually positive or negative. Right we take to be positive, left we take to be negative, up positive, down negative. Normally, that can change. Position, where an object is, distance, how far an object has traveled. For this, we'll use the symbol x or y, both lowercase, depending on if it's moving along the x-axis, we'll use x. We'll use y if it's moving vertically along the y-axis. Both of those are measured in meters. Displacement is the shortest line from an object's ending point to the starting point. Delta x or delta y, again, if it's on the x-axis, then it's x-axis, then it's delta x. If it's along the y-axis, then delta y. And again, measured in meters. They may seem like distance and displacement are the same thing, but they're not. So watch out for that soon. That delta thing, that's a Greek letter, capital delta, and that just to us means change. And change means final minus initial. A model is a representation of a situation or a phenomenon. Different models could be equations, pictures, assumptions that you're making. A point particle is a model that allows for analysis of an object's behavior regardless of size. A system is the picture we care about. Clock time, that's when something is. It's 3 o'clock now. And for clock time, we use the symbol T measured in seconds. Time interval or elapsed time is the number of seconds that have gone by. For this, we're going to use delta T, so the change in time, time elapsed, and again measured in seconds. Speed is how fast an object is moving. We're going to use the symbol lowercase v, and that'll be measured in meters per second. The average speed is our total distance divided by the time interval. So our average speed equals our distance, which is x, as we said earlier, divided by delta t, the time interval. And the measurement there is meters per second. Velocity is speed and direction of an object's motion. Again, we're going to use the symbol lowercase v measured in meters per second. Average velocity is our total displacement over our time interval. Our average velocity equals displacement over time interval measured in meters per second. Instantaneous speed or velocity is how fast an object is moving at that moment. We're going to include direction if we're talking about velocity. Total means the sum of all the parts, which is always positive. We use total, the word total, when we're talking scalars. Meanwhile, for dealing with vectors, we use the word net. And that's the sum of all parts, which could be positive or negative. If that option for negative exists, we're dealing with the net. Imagine asking for directions to the nearest gas station and the response you got was 3 miles. That means nothing to you, but if we change the response to 3 miles west, we can probably get to that gas station. Vectors have both magnitude and direction, like velocity or force, while scalars have only magnitude, like mass or temperature. Later in the year, we'll see that vectors are mathematical objects with components that are needed for describing quantities involving direction and magnitude, actually later this lesson, like displacement and force. For now, think of vectors as arrows. The length of the arrow shows the relative size or magnitude, and the direction it's pointed gives us our direction. Bigger arrow means bigger magnitude. Remember, the choice between vectors and scalars depends on whether direction matters in the situation. Scalars are used when only magnitude is important. Vectors are used when both magnitude and direction are important. Let's talk about position, or where are we? Position is where an object is. On the globe or on a map, we have latitude and longitudes. We can get an idea using the latitude lines, these ones running horizontally. And for us, we're like 30.3-ish, not quite halfway between 30 and 31 degrees north. And the longitude lines is 81.6, so this is 81, 82, 81.6 degrees west. We can be a bit more precise by using GPS. GPS, that's going to give us our exact latitude and longitude. Notice there is no mention of north or west. Instead, the direction is noted with positive and negatives. On a coordinate system, if we imagined this was the coordinate system, there would be a negative x and positive y, which is negative x, positive y. Greenwich, England would be x equals 0, so right along this axis. And we are in the northern hemisphere, so our equator would be our horizontal line. So we're in the northern hemisphere and we're west of England. Using coordinates in physics allows us to tell where something is or its position. Let's imagine each box here is 1 meter wide and 1 meter tall. This gives us a coordinate of -6, 5. We'll call this a person moving, but instead of drawing a person, I'm going to model it as a point particle. So this person doesn't take up any space. This frees us from having to wonder if we're measuring from the front of the toe, the back of the heel, the middle of the foot, etc. Now we've moved. How far did we move? This will be our distance. We can see the difference between the y values and notice we've moved 3 meters. We would say our distance is 3 meters. If we include the direction we have moved north, then our displacement is 3 meters north, including the magnitude, how much, and the direction. When we move again, here we can see the difference in the values. The y values are the same, but the x values have changed by 12 meters. We would say our distance now is 15 meters. Meanwhile, our displacement is the shortest distance from our ending point to the starting point. In this case, it would be square root 3 plus square root 12, which is about 12.37 meters. I can say 12.37 meters northeast, or just keep it as a positive because it's going up and to the right. Remember, we normally take up to be positive, right to be positive, left to be negative, and down to be negative. In physics and math, up and right, being positive is just normally how we do it. All right, let's keep moving. Now, this person moves down this way, and they've moved 14 meters south. So our total distance is 3 plus 12 plus 14 is 29 meters. Meanwhile, our displacement is going to be about 16.28 meters from our starting point. Pythagorean theorem, we're just subtracting out this. Let's continue it on, though. And now we've finally returned to our starting location, and the total distance here that we've traveled is 3 plus 12 plus 14 plus 16.28, which gives us about 45.28 meters. So our displacement, the shortest distance from our ending point to starting point, is 0. Meanwhile, our total distance is 45.28 meters. Displacement is the ending point to the starting point. Speed and velocity. Instantaneous speed is how fast you're going at any instant. An example is the speedometer in your car. Instantaneous velocity, how fast you're going and what direction you're going at any instant. Your GPS shows this. Average speed is the total distance traveled divided by the total time taken. It's a scalar quantity because speed is scalar and distance is scalar. Gives you an idea of how fast, on average, an object is moving without considering its direction. We have an equation for this, which looks like this from earlier. Speed is our average, v average. Our time interval is delta t, and the total distance is x. Look at our dimensions. The dimensions here are what we measure. Oh, we can actually... Okay. Dimensions are the physical quantities that are measurable. They are often related to official measurements called units. We have standard units in physics that we use: meters, seconds, kilograms, mole, ampere, Kelvin, and candela. We won't have to worry about Kelvin, we won't have to worry about candela, we won't have to worry about ampere, we won't have to worry about mole. So the three that we need to focus on are meters, seconds, and kilograms, and from those three, we're going to derive or make our own units. All of our derived units can be related to these standard units. Some examples include the Newton, watt, and joule. Remember, this formula here is giving you your average speed. The average can change if you're going different speeds for different amounts of time. Don't forget how to take an average.
Memorize this equation because it's not on your equation sheet.
Good advice. For the average velocity formula, notice that the v average now has the vector notation above it. That indicates its velocity. So direction matters. Same with our x. This is now delta x. This is our net displacement. Still measured in meters, but it's net displacement divided by our time interval. So if our net displacement can be negative, that would mean our fraction on the right becomes negative, which means we can have a negative velocity. Normally what that means is our velocity is in the opposite direction, opposite of whatever. It could be just that it's moving to the left instead of to the right. It could be that it's moving down, something like that. We say total when dealing with scalar quantities, or we expect the answer to be positive, and we say net when using vectors, or the answer may be positive or negative.
Memorize this equation because it's not on your equation sheet.
Okay, again. For real. All right, so when do we use it? We use speed, average speed, if there's no direction needed, or if you know the total path length that was traveled. Remember, the total path length we call distance. Use average velocity if you know the displacement, or you need to mention the direction. Displacement is your final position minus your initial position. Read the question carefully because sometimes you'll be asked for speed and sometimes you'll be asked for velocity. Just make sure you know what the question's asking of you before you answer it. In physics, we use subscripts to tell the difference between similar looking symbols VI and VF. VI would be the initial and V sub F would be our final speed. We can do the same thing with X. X final or X sub F minus X sub I for initial, or X sub 0 or X naught